Hello, I'm Christoph Bergmeir. Welcome to my tutorial, Forecasting for Data Scientists, a random walk through the random forest. Let me start off with a bit of introduction, a bit of background about myself. So in 2008, I graduated in computer science from the University of Ulm in Germany. Then in 2013, I finished my PhD in computer science and IT at the University of Granada in Spain. The topics were time series forecasting, also forecast evaluation, a bit of cross-validation for forecasting. Then I also did a research stay at Monash University with Rob Hindman. And I also worked on some more applied projects in forecasting for fault detection in wind turbines, forecasting for pest outbreaks in greenhouses. I also did a bit of predictive maintenance. Okay, so then I went on to do a postdoc, again in Granada, in predictive maintenance for railways. And since 2014, I'm at Monash University, first a research fellow, then a lecturer. And now I'm currently a senior research fellow on a 3 years fellowship to focus solely on time series forecasting. Here the applications I work on are mostly renewable energy production forecasting, like wind and solar, some energy demand forecasting, energy price forecasting, and I also do retail sales and demand forecasting. So you see, I've done quite some forecasting in the past. And the applications I would usually work on are, as mentioned before, sales forecasting in the supply chain and retail, doing forecasting in energy, like demand prices, renewable energy production, also a bit in building efficiency. I've also worked a fair bit in predictive maintenance in roads and railways, not so much in mining. That's something I'd also like to work in. So that's what I forecast. However, what people think I forecast is usually a bit different. So when I go to a party and I tell people that my job is forecasting, then usually one of two things happens. So either the people ask me like, oh, so you do weather forecasting. Or the other thing, people say, oh, so you can predict the stock market and we all get rich. And then I usually say, well, the weather forecasting, there's a lot of domain knowledge and there exist all these specialized models out there. So we leave that usually to the meteorologists. However, the stock market forecasting, yes, that's totally what I do. Just bear with me a little bit. I'm going to tell you how we do it, and we're all going to be rich in no time. So let me start off with my favorite share. So this is the share price of my favorite share. You see it had a good run, and then at some point, just like something happened and it started to really go down, but now it's kind of going up again. And now if we want to predict that one, we will do something which is called an auto regression, which basically means a regression on itself, which is because the inputs and the target values, they are both from the same time series. And the way we do it is with this sliding window approach. So we're basically sliding a window over the time series, taking what we see here as blue dots as inputs and the orange dots as outputs. And now obviously we can just stack that together. We get this embedded time series matrix. And now we just use our favorite regression technique from machine learning to train a model. Obviously we can partition our data into a training and a test set, and then we train the model, and then we can test it on some future data. And I've done that here for you, for example, with a neural network. And what you see is that on the test data, actually, wow, that worked really well, right? So it's totally nailing it, like totally following the signal, seeming to get everything pretty much right. So, okay, that seems to work, but however, we are scientists, so we know you can't just build one model and be happy, but you have to build a couple of models and then compare them against each other. So I just trained a random forest, a support vector machine, and a neural network, and I'm showing them all here. And you see, well, it seems that the random forest maybe doesn't work so well. That's the blue one. But in general, it's quite difficult to say which one works better, and they all seem to be reasonably okay. So let's have a look at some errors. So I've calculated here the mean absolute error and the root mean square error. And we see, well, on the RMSE, it seems the neural network is best. On the SVM, actually, on the MAE, actually, the SVM is best with quite a bit of difference. So, okay, so the SVM seems to work a bit more robustly. So done. Let's just write a paper, novel, robust SVM method for stock market prediction. And now let's just go out there and all get rich. Okay, well, sorry. So hold on. Regretfully, I have to now break the news to you that, yeah, I reject papers like those probably once a month. And we are not all getting rich, at least through doing this. I'm very sorry. So why is that? Let's just generate some random numbers. So here I've put you down some R code, which basically just generates 1,000 normally distributed numbers and plots them. Okay. And now, what about we just sum them all up, right? So let's just do a cumulative sum over these randomly generated numbers. And now I think this plot probably looks a bit familiar to all of you. So that's what I before told you is a share price. Actually, it wasn't a share price. It was just what we would usually call a random walk. So why is this called a random walk? Because basically at every point in time, you take a random step in either direction, which is basically on any given point in time, you just add a random number to your current value. And that's what we get. Good. So how would we predict such a thing? Well, I mean, these random numbers, because they are normally distributed, and I've actually generated them with a mean of 0. So the mean is obviously the best prediction for this random variable. And because the mean is 0, a 0 is the best prediction here. So now if we go to the random walk, now obviously the best prediction for our innovation in every step is a 0. So that means that the best prediction at any given point in time is just the last known observation, right? And this is called either a naive forecast, sometimes a persistent forecast. People also call it a random walk forecast. And this is provably the optimal prediction for this time series. Okay. And now actually, if you also have a test set, and for every value in the test set, you do that going forward. Now, obviously, at every point in time, your prediction is just the last known value. So that means that basically the series of your predictions is just the original series shifted by 1, right? So, yeah. And you see that actually looks it looks very good, right? Obviously, it follows directly the signal. So in this plot, it looks as if this method works very well. But the problem is that these plots usually tend to be quite misleading, because actually it obviously doesn't matter the error in the horizontal line, but the error in the vertical line, and they actually can be quite big. So yeah, good. Now let's calculate some errors. We now actually see that the naive forecast is best on the RMSE. On the MAE, our SVM is still best, so our paper is still not lost. We can still try to go ahead with it. But anyway, so you see here two things, right? So the first thing is what we've done so far, all these model training and prediction, it wasn't good for anything, because the naive forecast is a provably best forecast, and it gets also the best results. And because of the small sample size, finite sample size, and so on, by just pure luck, obviously some method can be better, but that's not what we want. Good. So why do people do so much stock market forecasting then? Well, I think it's probably just because there's so much high frequency data available. So for people, it's very easy to get data. And it's also very easy to get like a clear motivation and a use case, right? So, I mean, it's about making money. So what's wrong with that, right? However, there are quite some cons to the stock market forecasting, right? The biggest problem is that a share price is not a function of its own past, but of its anticipated future, right? So basically just using a couple of lags of past values to predict the future, it's not going to work. You also have very low signal to noise ratio. And then there's obviously the efficient market hypothesis, which basically states that any information available will be already included in the price. So that means if the market is efficient, this type of forecasting with like values should not work well. And then there is Robert Engle, who got the Nobel Prize in Economics in 2003 for methods of analyzing economic time series with time varying volatility. So basically in this field of stock market forecasting, it's in the end, it's now all about predicting risk and volatility and not returns or the actual value. So basically you want to be able to predict the tails of the distribution. So yeah, just to sum up, predicting stock market returns from just a couple of lags, it will normally not work. And it really doesn't matter which method you use. You can come up with a very novel machine learning method, but it's just not working. Good. Now what I want to show you is just a couple of these random walks by changing the seed a little bit, because I still find it astonishing the rich dynamics you can get just from random walks, which is really just summing up random numbers. So you see here, it's kind of going up all the time, and there seems to be some sort of maybe even a seasonality here. That's the series I've already shown you. So, you know, I'm sure there will be many people that now say, oh, up here at this point in time, there was like this big crisis and then everything started dropping, and now here they kind of turned it around and now they are back on track, where no, it's all just random numbers summed up. There's nothing in here, right? Here another one that goes pretty much just down. This one is a bit more crazy, but here you see that has a lot of dynamics, or yeah, almost like business cycles or seasonality, something like that. Good. So that brings us to a bit of the broader question of what can we forecast, right? So the fundamental assumption in forecasting is always that the future depends on the past. And that means we need past data and past experience to extrapolate from. However, predictability varies widely. So just because you have a lot of data, that doesn't mean a lot. I've shown you the stock market example, but let's talk about some more examples. For example, next Monday is time of sunset, right? That's very predictable because the sun is very predictable and physics is very predictable. TV schedule in 2 weeks' time, that's very predictable because we want it to be predictable, because people work towards it being predictable. On the other hand, something like next Saturday's lottery numbers, right? I can give you the last 20 years of lottery numbers every Saturday and you can build your model, but you know, you shouldn't be able to extract anything from that. And these financial variables, stock prices, but also exchange rates and some others, they are kind of in between. So they're obviously not purely random, but still there's a lot of mechanisms that work against patterns and against predictability. So some important factors for predictability are: how well do we understand the underlying phenomena? How much data do we have? Will the forecast affect the future? And especially in our case, where we use mathematical models for forecasting, I think it's very important to model adequately the repetitive patterns in the data, but do not let distract you by the noise and the unique unforeseeable events, right? So what forecasting for us is really about is to separate the time series into a part with predictive value and a part of noise. Some other considerations, so forecasts are always wrong, and that means that you should really always use prediction intervals to quantify the uncertainty. Another thing that I learned throughout my career is that if you don't have to forecast, then it's better to really not forecast. So what does that mean? So usually forecasting is done for decision making. So ask yourself, can I make that decision without the forecast? Can I more focus on resilience of the decision making? So what I've seen failing a couple of times is if you say, well, if I had a perfect forecast for what the weather will be in 2 weeks' time, then I could make now an optimal decision. So usually your forecasts are not going to be that good, so that the decision making is not going to work very well based on that forecast. On the other hand, situations where I have seen forecasting really work very well and where it gives you the biggest wins is in situations where you are already using a usually quite bad ad hoc forecast in your decision making, right? So that's probably true in retail, right? So in retail, to make a decision how much to buy, you will always need to predict how much you're going to sell. And now the question is just, well, do you just use a naive forecast to predict how much you're going to sell, or do you try to do something more sophisticated? Good. This concludes this first introductory part of the tutorial. I'm now going to talk a bit about traditional statistical univariate forecasting techniques. But actually, before I do that, let me start off with just a bit of forecasting terminology so that we're all on the same page with this. So a lot of the terminology in forecasting comes from statistics, but there's also some terminology only in forecasting. So for example, when I say model fitting parameter estimation, that's what we in machine learning would call more model training. In-sample is a training set, out-of-sample or OOS is a test set. A forecast horizon is the target variable. Let's say I want to do a 1 day ahead forecast, 30-minute ahead forecast. Forecast origin is from where you do your forecast from, which is usually the last observation. So you say, I want to have a 1 day ahead forecast. So that means today's value is the last value I can use. So that's my forecast origin. A rolling origin now basically just that this forecast origin changes for every point in your test set, right? Today I make a prediction for tomorrow. Tomorrow I make a prediction for the day after tomorrow. Fixed origin is where the forecast origin is fixed. Today I predict for tomorrow and for the day after tomorrow and for the day afterwards. Or today I predict for the whole next week. Good. Forecast combination, that's what we in machine learning would usually call ensembling. Lags are past data, right? So basically a lag 1 means if I'm today, a lag 1 is yesterday. So it's always kind of the value before. On independent variable, regressor, covariate predictors, that's features or inputs. Dummy variables, indicator variables, that would be usually called in machine learning a one-hot encoding. Seasonality, seasonal period, that's like a cyclic change in the mean of the series. And the assumption is usually that its length is known a priori and it will not change in the future. And the trend, again, it's a smooth change in the mean of the series. Good. With that, we can, look at some traditional forecasting methods. So we've actually already seen in the introduction 2 very simple forecasting methods. One is a naive forecast, and the other one is a mean forecast. Now, it turns out these two are actually 2 very extreme cases. So the naive forecast only considers the last observation and none of the others. Whereas in the mean forecast, we calculate the mean over all observations, so all past observations are weighted equally, right? However, in forecasting, a central assumption is often that the more recent past is more important than the more distant past. So now there's this idea, well, what about we don't weight them all equally, but also we don't look only at the last observation, but we have something like we weight the last observations more, and then we have it kind of tapering off. So an idea is to do this with an exponential decay, right? So you have an exponential decay in the weighting of past observations, and this brings us to a method that is called exponential smoothing. So simple exponential smoothing is exactly that. You have the past observations, and you have exponentially decaying weights. So here in red, I actually show you these decaying weights. Well, I shifted them away from 0, just that the plot is more understandable. But yeah, so they have a weight decay of 0.62, and now you see the forecast. It's not exactly just the last value, but a bit shifted. Good. Yeah, and now exponential smoothing, as it's used nowadays, it's basically just applying this idea to different components. So usually you decompose the series into a level, seasonality, and trend, and then apply this exponential smoothing idea for these components separately. Exponential smoothing was first introduced by Holt in 1957, and then by his student Winters in 1960. That's why it's also called the Holt-Winters approach. And it actually was used for a long time as a relatively ad hoc method without any theoretical underpinning. And that changed in 2002 when Hindman et al. Gave it a solid statistical foundation in state space models. And if you're wondering, the term ETS stands both for exponential smoothing, but also for error, trend, and seasonality, which are again these components of the exponential smoothing model. Good. So that was one very prominent forecasting family, the exponential smoothing. Now let's look at another one, which is the Box-Jenkins modeling, presented in a seminal book in 1970, which is the autoregressive moving average model, or ARMA, AR, ARIMA, this type of modeling. So it's a linear model in the lags and in the errors. So the idea is you have basically here your xt, and then you have like xt minus 1, t minus 2, and so on. And you just build a linear model on those. And now you also have your errors at time t, t minus 1, and so on, and another linear model on all of them. So it is a linear model. However, if you've ever tried to fit an ARIMA model, you would ask yourself, well, where do I actually get these errors from that I need in the fitting? So it turns out that you need to estimate some initial conditions and then actually step through the whole series, because you always need the prediction for a value so that you can calculate the error at this point in time. And in ETS, you actually also need to step through the whole series. So it turns out it is linear in the lags and the errors, but there is no closed form solution. You actually need a nonlinear fitting procedure. And by default in R, that's actually a BFGS optimization. So it means that fitting of these models can actually be slow in long time series, right? So, but that's because of the MA part. So obviously if you have a pure AR model, linear, then it has a closed form solution. It's very quick. Yeah. Good. So, well, maybe you've heard about an ARIMA model. So what does the I stand for? Well, the I stands for integrated. So we've seen the random walk before. So now the question is, do we want to model the values directly, or do we want to model just the change to the last value? right? And this is usually done to address non-stationarity. And it's more like a pre-processing step. So you basically just do differencing of the series, and then you just do the ARMA model, right? So the idea is, well, this differencing hopefully makes the series stationary, but the problem is we lose the information about the scale. So we lose some information in the modeling, actually. Good. There's another result in the literature that actually any stationary AR1 model has an equivalent MA infinity model, and any invertible MA1 model has an equivalent AR infinity model. So what does that mean? That actually means that we can approximate the MA part of the ARMA model with a higher order AR part. And in practice, this higher order is often not so high, actually. I mean, in econometrics, often 5 is already like seen as a quite high order. So I see so the ARMA model can actually be seen as more of a reparametrization to get fewer parameters and a smaller input window, but at the cost of more complex nonlinear model fitting, and that you need to step through the series. Now there is this standard implementation of these methods from the forecast package in R. So this is a very, very well-known implementation, and it's used as a standard implementation. There's these two functions, ETS and auto.ARIMA. And actually they are both wrappers for automatic model selection of both ETS and ARIMA. So the ETS function, it fits 15 models with different error, trend, and seasonality. And the auto.ARIMA, by default, it fits models up to order 5, both in the, well, P and Q, so both in the AR and the MA part, and up to 2 differences. And then you just choose the best model according to the corrected AIC. And yeah, so these functions are widely used standard benchmarks, and they are very often very competitive, like surprisingly competitive. Okay, so we've now seen the traditional approaches of ETS and ARIMA. Now let's delve a bit into a brief history of forecasting competitions next. So there is this competition series called the M competitions. And actually in my discussion here, I'm following mostly a very nice paper by Hindman from 2020. So in 1971, Spyros Makridakis, the M competitions are named after him. So Spyros Makridakis and Michel Hibon wrote a paper in the Journal of the Royal Statistical Society where they benchmarked a bunch of time series methods against each other on a set of 111 time series. So it was the first time that anybody tried really such an empirical evaluation of these methods. And what they found, what was kind of a surprising finding, was that simple methods, and for them simple methods were things like a seasonal naive or simple exponential smoothing, they worked often better than an ARIMA, which was considered a complex method at the time. So back then when you wanted to, or it's maybe still the case, I'm not sure, but basically when you wanted to publish a paper in the Journal of the Royal Statistical Society, there was actually like a lecture attached where you had to defend your paper in front of a very knowledgeable audience. And in that audience, there were really like very well-known statisticians of that time. And this discussion, it's actually published alongside with the paper. So you can look it up and it's quite interesting to read. So for example, Chris Chatfield, who also wrote a well-known book in time series, said, I find it hard to believe that Box-Jenkins, if properly applied, can actually be worse than so many of the simple methods. And in general, in the discussion, there was a strong belief that there is a true underlying model, a true underlying data generating process that you just need to discover. And then this underlying model will necessarily also give you the best forecasts. So because ARIMA didn't work very well, consequently the discussants questioned the ability of Makridakis and Tibon to use these models properly. Yeah, so some of the comments are getting even quite personal around that Makridakis and Tibon don't know how to use these methods. And also the discussants in general didn't agree with defining that forecast combination works well. Nowadays we would call this ensembling, as I said before. Good, so then basically Makridakis said, well, if you tell me I can't really use these methods properly, I'm going to organize a competition. And then everybody can just put in, use their favorite method and submit forecasts. So the M1 competition was born, and the results were published in 1982. This time it was a 1001 time series, and the results largely confirmed the earlier results. Because the best method was a seasonal naive combined with SES, forecast combination worked well, and after this forecast, and it had really kind of profound implications, because after this competition, forecasters focused much more on out-of-sample accuracy rather than on model properties. And forecasting actually emerged as a field independent from time series analysis, because people now understood that, well, wanting to really understand the dynamics of a time series or wanting to give you the best prediction, it's actually not the same thing. It's two different problems. Then nearly 20 years later, Makridakis and Tibon organized the M3 competition. There was another M2 competition that was a bit different, so I'm not covering it here. The results are published in a paper in 2000. And this competition again had as a central conclusion that complex methods do not necessarily outperform simple methods. And again, ETS and ARIMA were the complex models, and simple models were models more like a random walk with drift. Then there was one neural network that participated in the competition. However, it was quite bad. And the competition was actually won by a method called the theta method, which was later shown to be an average of a linear regression and a simple exponential smoothing with drift. Then after the competition, this M3 competition dataset went on to be the benchmark dataset in forecasting for almost 20 years. And there was a lot of focus on this dataset, probably too much focus, because people were really kind of honing in on this dataset. And so throughout the years, there was always quite a controversy of whether machine learning methods or statistical methods are better for forecasting. Because from the knowledge from all these competitions, right? So M1, M3, but there was also the NN3, the NN5 competitions. Forecasters had the feeling they knew that simple methods work best. And on the other hand, there were these machine learners that knew that neural networks work best because, hey, well, it's a neural network, it's a universal approximator, of course it's going to be better than something so simple. So that actually led to thousands of papers in neural network journals and other places published, which are, a bit similar to what I outlined in the introduction, like a novel method X for stock market forecasting with cherry-picked data set, no proper benchmarking, and not very solid. So that was kind of a quite well-known fact in the forecasting community. So Makridakis and his colleagues in 2018, he wanted to kind of point that out in a paper where he benchmarked machine learning methods against statistical methods. The paper is called Statistical and Machine Learning Methods, Statistical and Machine Learning Forecasting Methods, Concerns and Way Forward. And not surprisingly to forecasters, the machine learning methods lost, because they had lost in many competitions before. But now interesting, so this paper, it's published in PLOS One, because it actually got rejected at 2 to 3 neural network outlets beforehand. And the reasons for rejection were along the line that there are many machine learning methods that have proven to overcome the results provided. This is what the editors and the reviewers said in these journals, but they didn't provide any results in particular, right? So Makridakis was somewhat understandably quite upset over this, and he did what he seemingly does best, organizing a competition, the M4, so that machine learners could submit their forecasts and really show that machine learning methods work better than statistical methods. Yeah, so I hope this history, it explains you a little bit why the forecasting field, it really kind of got a bit hung up on this controversy of whether machine learning and statistical methods work well. And you will notice that if you try to publish a machine learning methodology paper in forecasting places, that they would very often be very critical. However, I still find that really surprising, because forecasting emerged from statistics just in the same way machine learning emerged from statistics, if you think about it, right? So this focus on out-of-sample accuracy and not model properties, that's exactly what machine learning, what distinguishes machine learning from statistics, I would argue. And consequently, some things were discovered in both fields independently. For example, forecast combination is well known in the forecasting, is well known to work in the forecast community since a seminal paper from Bates and Grunger in 1969, well before ensembling came up in machine learning in the 1990s. And then we have in forecasting this kind of focus on simple methods, which in machine learning, I think, is quite similar to the regularization. So I think really the field of forecasting and machine learning, yeah, it's not about kind of which one works better, but they have so much to learn from each other. So I really encourage researchers from both fields to work together. Good. So yeah, as I had mentioned, there was then the M4 competition in 2018. It was this time 100,000 series across many different domains. It was also more granularities, hourly, daily, weekly, monthly, quarterly, and yearly series. As a novelty, you also had to predict prediction intervals. The results are published in a paper from 2018. And I guess most forecasters expected here that a combination approach of statistical methods would win, right? Because that's what we had seen in competitions before. However, as a big surprise, these methods got second and third, and actually the winner was a method called RNNs, which stands for recurrent neural network and exponential smoothing, which is a hybrid between an RNN and ETS, by Slavik Smyl, published in 2020. Yeah, so in the forecasting community, it was definitely a big surprise to many people that a machine learning model could win. For me, it was not that much of a surprise. And that's for a simple reason, because I got beaten by Slavik Smyl 2 years earlier in a different competition. It's called the CIF 2016 competition. So that was a very small data set, 72 monthly time series, so also very short time series. Some of them only 22 data points long, right? So I went into that competition. I ran just plain ETS from the forecast package and a method that I had developed a bit earlier together with Rob Heidman called backed ETS. And I was quite sure that backed ETS would be able to win that competition because it was marketed as like a computational intelligence competition, but the data set, to me, it seemed like, well, statistical methods need to be able to win here. So I was quite surprised that, so the back DTS didn't do bad, but it won several subcategories, and it was also winning on the median sMAPE. However, on the competition metric, the mean sMAPE, back DTS actually got 9th place, but plain ATS got 3rd, right, which is quite remarkable place. However, 1st and 2nd place were LSTMs submitted by Slavik Smul. And so now what he did was he had globally trained them across series. Good, that brings us to our next point, global models, which is really a very important paradigm shift. Okay, so the name global models was actually introduced by Januszowski in 2020. So the idea traditionally in forecasting was that one time series should be seen as a data set. So you build one model per time series. And now what happened is that low sampling frequencies and non-stationarities, like structural breaks, usually make that we just don't have enough data to fit a quite complex machine learning models. So simple models obviously work better. If you have 20 data points, there's just not so much to fit. And the M3 and M4 data sets, they were put together under this paradigm. Very different series from very different domains, just put together into one data set. However, now we really see this paradigm shift. So now people don't look at a single time series as a data set, but as a set of time series as a data set. For example, a set of series from retail kind of sales across different products, in energy, smart meters from many different households. And now what we would do is we would build a model across the series. And while this is known under some different names, I call it global modeling, other people would call it cross-learning, multitask learning, also pooled regression is very related. And now it turns out that if you do that, now suddenly you have enough data because you have more series. And now you can actually build quite decent machine learning models on these series. Because if you think about it, if you build a local model, one model per series, maybe with ETS you are fitting only 5 parameters for a series. But now if you have 10,000 series that you want to forecast, you obviously fit 5 parameters per 10,000 series, so you fit 50,000 parameters in total. So maybe try to fit a global model instead with just 5,000 parameters, right? So the main thing here is that the overall complexity of a set of local models obviously grows when the data set grows as you get more time series, whereas the complexity of a global model just stays the same. You can use more series, it doesn't matter. So that means global models can afford to be more complex. And now you have different ways to add this complexity in. Actually, you can give the series longer memory with longer input windows, which means more lags. Or obviously you can make your models more non-linear and non-parametric. And there obviously all this machine learning comes into play. Neural networks, gradient boosted trees. And another thing, another idea that some authors have followed as well, I in my research, is to do data partitioning, to train the model not on all of your series together, but to kind of partition them in certain ways. Another important point I want to point out is that global models are not multivariate models. So very often when I talk about global models, people then say, oh yeah, sure, so it's a multivariate model, right? And I say, no, it's something else, because a global model, it learns across the series, but then it predicts every series in isolation. So I think this difference is most understandable when you look at a data set that is not aligned in time, where the series have very different lengths, one starts 10 years ago, one starts 2 years ago, and the M3 and the M4 data sets, they are actually exactly put together like that, right? So there you can't train a multivariate model where like at one point in time, all your 10,000 series, they all move together. No, they can be quite disparate. Yeah, and they don't take into account interactions between the series because every series is predicted in isolation. Okay, so I mean, I've talked about that global models are kind of getting quite popular since 2016, but to be fair, that's not quite when they started, so they actually date back to the early 2000s and earlier by some work, and then there was actually a very good paper in 2015 from Trapero et al. About pooled regression, where the idea is just to have a linear regression, linear autoregression with your legs, and now basically you just stack these matrices together and then build a model across all the series. Then obviously 2016, the work by Slavek Smyl. And then in 2017, there was this paper, also very important paper coming out of Amazon, and there's a lot of very good work in this area coming from Amazon. So Deep AI in 2017, then the Wen et al. Paper 2017, and also some early works in my research group from 2017. And then after 2018, it really kind of took off, and there's now a lot of research that uses this idea of let's build a model across the time series. And another important development to mention is Kaggle competitions. So there is actually now a quite good overview paper from this year as well, 2020, but it has gone quite unnoticed in the forecasting community. But there were a couple quite relevant forecasting competitions held on the Kaggle platform. So for example, in 2014, 2015, there were like a couple of retail sales forecasting competitions and the Wikipedia web traffic forecasting competition in 2017. The Corporación Favorita grocery sales forecasting in 2018, and the restaurant visitor forecasting competition in 2018. And very notably, all these competitions were won by global models. So already in 2014, competitions on Kaggle were won by global models when, in the forecasting community, that would still take another couple of years until they were really known, and the latter four that I mentioned here, they were actually won by just globally trained gradient boosted trees and neural network models or ensembles of those. And then consequently, the M5 competition that was held this year in 2020 on Kaggle, it was a data set from Walmart about retail forecasting, also like a couple thousand of series across different products and different stores. So that competition was heavily dominated just by light GBM. Also methods like Deep AI and NBeats were successful, and actually a team of my students, they were also quite good, so they won a Kaggle Gold, ending up 17th place in the competition that had over 5,000 participants. And what my students actually did was they used an ensemble of just globally trained light GBM and a globally trained linear model, which is also called a pooled regression model. So these global models, they have shown success, like really to a nearly surprising, unreasonable degree. And the idea in recent years was always that the series that you learn across, they have to be similar or related in certain ways. They all have to be product sales or that share kind of the same seasonality or something like that, so that we can learn something useful across them. Now, there was this big discussion in the forecasting field. What does related mean? And we now think that related should mean they are similar in terms of their data generating process. It certainly doesn't mean that they're just correlated or something like that. However, there is this really good paper by Montero, Munson, Heinemann from 2020, where they argue that global models can produce the same forecasts as local models without any assumptions about similarity. So they actually are able to show this. So that means the series actually don't have to be related. I think the idea is that instead of fitting one complex pattern across the series, a global model actually also works quite well if the patterns are quite simple and different across the series. And this is actually a quite remarkable result, because similar results, for example, in multitask learning, don't exist. Yeah, so there is now kind of some theoretical work around why these global models work so well. So we're getting a bit of a grasp for this, what's happening here, but still they are a very active area of research and very interesting. The next section is about machine learning methods for forecasting. So they are nowadays often a good option. So we've just seen that global modeling across series works really well, and this type of methods work really well as global models. But we can also just apply them to a single time series as long as this series is long enough. So nowadays, very often we actually have such long series due to finite granularities. Just think about secondly, minutely, or half-hourly series that are recorded over years, and you get thousands of data points even in just one series. And very often we would also have additional metadata available, and obviously machine learning models can be very flexible to learn across this metadata. So the usual setup how to train a machine learning model is basically just a nonlinear, non-parametric autoregressive model, which basically means you just take a window. As we've seen before, you have some lag values in that window, and then you predict the next value, because then you can basically just use your favorite machine learning method for regression out of the box. And we've also seen before that this can then also approximate an ARMA model. You just need to choose the input window larger than how you would have it in the ARMA model. However, there is a problem that is non-stationarity. So non-stationarity means that the data distribution changes over time. And if you think about it, actually many or even most of the real-world problems have a time component, and they do have changing distributions. What do I mean by that? So just about somebody tells you you have a task to detect cars on the street with imaging data, like video data, but they give you a training data set from the 1970s to detect cars nowadays, right? So in the 1970s, obviously cars look different, they had different shapes, different sizes, and so on. So probably training on such a data set wouldn't work very well to then run it on today's data, just because the data distribution of what a car looks like has changed throughout time. However, in time series, these problems of non-stationarity are usually much more explicit, and they do have more impact. So just going back to the example that I showed you before with our stock market price. So it actually took me a while, and I need to like fiddle around a bit with seed values to find a model where these very simple machine learning models would work, because one thing that can often happen is what you see here. So you see here is basically where the training set ends and the test set starts. And now you see in the training set, you've actually never seen values above about 60. So now obviously, for example, a method like a random forest, I mean, if that has never seen a value above 60 in the training set, it's not going to predict a value above 60 in the test set. And same for the support vector machine and the neural network. They are just that the data goes up here. They just have never seen that, so they are not able to model this properly. Yes. However, non-stationarity, it's a bit like non-linearity, and I'm going to explain you what I mean by that. So there's this joke that I like quite a bit, which goes that dividing the world into linear and non-linear is a bit like dividing the world into bananas and non-bananas, right? So on the one side, you have like linearity, a very clear-cut concept. And then non-linearity can mean so many different things. It can really, mean pretty much anything that is not linear. And so just there are so many different forms of non-linearity. There are also many different forms of non-stationarity. Again, stationarity just means the distribution doesn't change. Non-stationarity means the distribution changes, but it doesn't tell you how the distribution changes. So a couple of examples for typical non-stationarities in time series could be a change in mean. If that changes periodically, it's usually a seasonality, or if it's a slow, smooth change, we would see that as a trend. You can have a change in the variance, that would be then heteroscedasticity, or you can have the random walks that have unit roots, so the random walks that we've seen before. So now how can you make a series stationary? So because in econometrics and finance, many series are actually close to the random walks we've seen before, their differencing is a common tool to achieve stationarity. And we talked about the differencing before in the ARIMA modeling. However, differencing only solves some forms of non-stationarity and not others. So because out of these econometrics and finance literature, differencing is always seen as a way to tackle non-stationarity, there is now sometimes a notion that with differencing, you just get rid of non-stationarity. And that's not true. It only works for certain types of non-stationarity. Another type of non-stationarity would be structural breaks, and obviously integrated behavior like a random walk. And structural breaks are very, very different types of non-stationarities that need to be dealt in very different ways. If we do differencing, we do lose information about the scale. So that's a drawback of the differencing. However, you can just have an additional input. For example, you take the log of the original scale as an additional input, which is kind of a workaround of losing this information. And differencing can also help to make machine learning models more robust. So I think that's a quite important notion, that sometimes people think ARIMA is for non-stationary data, machine learning methods work only with stationary data. That's not true. The only thing that the ARIMA does to make things stationary is differencing, and you can just do differencing on your input and run your machine learning model of choice, and you achieve the same thing. Now, another non-stationarity trend. How could you deal with trend? Well, you could obviously detrend your series, which means you fit the trend and then subtract that trend. However, there's the problem that it is not really well specified what a trend actually is. So usually it's seen as just like a smoothed version of the original series. So that leaves you with the problem that you still need to forecast that trend. So you're not gaining much because you still have a non-stationary component that is now maybe smoother, but it's still there and you still need to forecast it. Another thing that people often do is a logarithm or Box-Cox transform, right? So a logarithm would obviously make exponential trends linear. It's also often used to stabilize the variance. And also a Box-Cox transform, it can be seen as like a generalization of the logarithm. So basically you have this parameter lambda, and if lambda is 0, you take the logarithm, and if lambda is 1, you see that here you get essentially the identity. And now if lambda is between 0 and 1, you get something between an identity and a logarithm, which means, yeah, so the logarithm is sometimes seen as a very strong transformation. So basically, if you don't need such a strong transformation, you can have a transformation that achieves the same thing, but not in such a strong way. And obviously the problem of strong transformations is that errors that look small after this transformation can be huge if you invert this transformation. So basically your loss function maybe thinks that's just a small error, but then after back transforming, it's actually a huge error. That's the problem of such a strong transformation. However, a problem of the Box-Cox transformation is that this parameter lambda, it's actually not so easy to choose. So you have here another hyperparameter you need to tune. There are some automatic procedures how to tune the lambda, but yeah, but it's not easy. Another quite nice approach how to deal with trend is window-wise normalization that was first introduced by Smul and Kuber, and then we also picked that up in a work my student Kasum Bandara in 2017. So here the idea is basically you have your input and output window with which you train the neural network, and now you normalize the input window, and you have different ways of doing this. But for example, you can in the original work there was actually done so they would extract the trend with a decomposition method, and then they would just divide this whole input window by the trend value of the last value here in that input window. Yeah, so this method is actually a quite nice method to avoid saturation issues of the sigmoid and tanh activation functions, as we've seen before in the example. It can be seen as similar to batch normalization because you normalize each window by itself. And what you actually achieve with that is that now instead of saturating just on the absolute values of the training data, what we've seen before, like if you go above 60, you just have never seen that. Now you're not saturating on that, but now you're saturating on the absolute value of the steepness of the trend in the training data. So that means your model is now not going to model any trend that is steeper than what you've seen in the training data. And we now actually argue that this is actually a good thing to do because that makes your forecasts more conservative and you don't predict like just very, very strong trends. Yeah, and as I said, you can like extract the trend value of the last data point in the window. Another thing you could do is just calculate the mean over this window and divide by that. Yes, and we have actually done some experiments, some simulations where we could show that actually with doing the logarithm and then doing this window-wise normalization, an LSTM or neural network can actually predict really strong trends. So what you see here is that in black we have the training data, and now in blue that's all the test data. We are learning across series, so you see here many series, and here in green, you can't see it very well, but it's just kind of you're following quite nicely this blue line. So in green, that's our predictions, and it's not a rolling prediction, but it's just so the LSTM predicts this whole output window at one go. So you see it's really able to predict the trend, this very steep trend forward. Very different to what we've seen before, where it would just kind of stop at the highest value it has seen. So just some more considerations or kind of expert knowledge, domain knowledge about trends. So as I said before, be careful with very strong trends, right? Because exponential trends will slow eventually. So as an example, let's say you are trying to model how many people will be using Facebook. A company like Facebook, they have definitely had exponential growth over many years, or Apple or other such companies. But we know, so it's not in the data, but we know as expert knowledge that this trend will slow eventually, simply because there won't be enough people in the world anymore to get more Facebook accounts or to buy more Apple products, right? So exponential trends will always slow at some point. Another interesting thing is that even a linear trend is actually quite often a quite bold assumption if you go very far into the future, right? So even linear trends are very often slowing down at some point. And that's why actually there was, in the traditional forecasting literature, you find this concept of damped trends, where you have a linear trend that is just slowing down. And they are actually often not justified from the data. It's just a way to be conservative about your forecasting. And as I said before, it turns out that forecasts should always be conservative. It's always a good idea to not make wild guesses that then don't come true. The next type of non-stationarity we want to look at would be seasonality. So how to model seasonality. So there were some discussions in the literature whether a neural network can model seasonality directly or not. Early works suggest that a neural network can model seasonality, mostly because of theoretical assumptions around that there are universal approximators and they should be able to do that. However, later work suggests that deseasonalization is necessary. And what we lately found is that, well, machine learning models, they can model seasonality well if they have enough data, right? So I think one very central thing to understand is that just because a neural network can learn something in theory doesn't mean that it will learn it in practice. So even though the neural network has the capability to learn the seasonality, if you don't have enough data, it probably just won't. Now, what does mean enough data? Well, think about having just 2 seasonal periods versus having 20 seasonal periods, for example. Another thing is that an assumption in forecasting is usually that we know the seasonality beforehand and that it is perfectly valid to just extrapolate it infinitely into the future. So about seasonality, we can be very confident we know it beforehand and we can be very confident it doesn't change. So to a forecaster's mind, there is nothing wrong to just say, I have a weekly series, I have a daily series, I assume there will be a weekly seasonality, which means I have a cycle of 7, and that's not something I need to discover from the data, that's something I just assume. And I also assume that in 10 years' time, still a weekend is going to be a weekend and a weekday is going to be a weekday, and they're going to show certain patterns. Because very often what you see is that machine learners spend a lot of time in kind of automatically discovering the seasonality and so on, when in practice that's very often not an issue. Yeah, so how can we model the seasonality? Well, so again, if you assume that's something that you know and that you can put into the model, then you can, for example, use seasonal indicator variables. You could just have a categorical variable, a categorical feature that tells you if is this Monday, Tuesday, Wednesday, and so on. And then you can have that as a one hot encoded variable. And this would be then in forecasting and in statistics called a seasonal dummy variable. However, you obviously have problems if there are many seasons. So a weekly seasonality, a weekly seasonality in a daily series, you obviously just have Monday to Sunday, so 7. But think about seasonality, something like a weekly, you have a weekly series with a yearly seasonality. So now you have 52 different weeks. And so then this one hot encoding can obviously blow up a bit. So one way around that is you just have like a continuous seasonal indicator where you basically just say, well, Monday is a 1, Tuesday is a 2, and so on. So it goes from 1 to 7, and then or from 0 to 6, and then you drop back. So you get this kind of sawtooth shape in your indicator variable. But now you have the problem that there are these abrupt changes where you just jump from, let's say, a 6 down to a 0. And yeah, for example, well, if this was a yearly seasonality, you jump from December to January. So then basically January to February has a distance of 1, February to March has a distance of 1, and then December back to January has actually a distance of 7, which is not true in the real world. In the real world, December is from January just as far away as January is from February. So in order to get around this problem, what you can do is you have kind of smoother functions that could be modeled like this, and these are actually, so you would use here sine and cosine waves for that, and this is a model type of modeling is now actually called Fourier terms. Yeah, more details about this can be found in Rob Hindman's book, standard book that I've cited here. So the idea is basically you have a sine and a cosine wave. T is your point in time that you want to, your current point in time. S is just the seasonal periodicity. So if you have a monthly series with a yearly seasonality, that would be 12 because you have 12 months in a year, or 7 days in a week, or 52 weeks in a year, right? And K is the number of sine and cosine pairs that you want to use. So the idea is that you need both a sine and a cosine to identify the value in the sense that think about it, if you only use here what's denoted as a green wave, now if you say this one is 0.5, you actually have here 2 different possibilities in the cycle to get to this value, right? So you need a sine and a cosine to uniquely identify this value in the cycle. And now it turns out that if you use more of these Fourier terms, not only one sine and one cosine, but more with also like shorter wavelengths, then that can actually control the smoothness of the seasonal pattern. Another way to deal with seasonality is to basically just remove it from the data. And there are these decomposition methods, for example, STL, MSTL for multiple seasonalities, STR, so STR is seasonal and trend decomposition with regression, STL is seasonal and trend decomposition doing low S. Yeah, so these deseasonalization methods, what they do is you have, let's say this is your data, and now they would just decompose your series into this trend component. And then if we do a multiple seasonality extraction, you would have, for example, this is a daily, hourly series. So you would get here this daily seasonality, which repeats after 24 values. And then you could also have a weekly seasonality, which repeats after 168 values. And then you have a remainder, which is just everything that is left and not subsumed into these 3 components. So, and these components would be additive. So basically adding trend, seasonal components and remainder together gives you your data. And again, here you see the trend is just some smooth version of the original series. Also keep in mind that here the scales are vastly different, right? So that's why this trend that here looks very prominent, like here it's it's probably much weaker in that data set just because they're on very different scales here. Good, these are just two different ways of decomposing. So you see they give you a bit different results, but should be comparable. And now, yeah, we apply such a decomposition, then we deseasonalize, and then we only feed the trend and the remainder component into our machine learning algorithm. I like the idea that this can be seen as a form of boosting. So you have this weak learner, which is your deseasonalization to model the seasonality, and then you have your machine learning model that trains on the residuals of the seasonal decomposition. You are effectively putting some expert knowledge into your modeling because now you assume there is a seasonality, it has certain repetitive characteristics. So what we have seen in our experiments is that this deseasonalization before feeding the data into the machine learning algorithm works well if you just don't have enough data to model the seasonality directly. Or if you have a data set in which like the seasonal component, where the seasonality in every time series looks just vastly different. Yeah. Because obviously these deseasonalizations work only on one series at a time, right? So if you now have a machine learning model that is trained globally across all the time series, then this method only uses the data from the time series. So it works well if the seasonalities are very different. Here I have an example, what I mean by that. So you see we have here a couple of different data sets. It's CIF, M3, M4, just some subsets of those, NN5, tourism. And what we see here is, for example, the M4 demographics data set. It's vastly different seasonal. So what this plot shows is just the seasonal component extracted from each series in the data set. So you see here that the seasonal components are just vastly different, also up here in the CIF data set. Whereas in the NN5 data set, they seem to be all the same. So basically all the series, actually the NN5 data set, that's ATM withdrawals, daily ATM withdrawals across different ATMs in the UK. And you see they all follow roughly the same pattern. So now what we found is that here you train a machine learning model across the series, it learns the seasonality perfectly well. Here you will have trouble, better to deseasonalize every series and then do the global modeling afterwards. Yeah. Exactly. So just some further considerations. As I've just discussed in the M3 and the M4 data sets, we actually see very, very different seasonalities mixed together, and also the series are not aligned. But in a real-world data set, this will very often or normally not be the case. You would see much more like what I've shown in the NN5, that all the series follow roughly a similar seasonal pattern. And then in that situation, actually just using some seasonal indicators of Fourier terms works well. But again, take into account that on something like the M4, you can't use Fourier terms because if the series are not aligned, they have all different start dates, different end dates. And the problem with M4 is you don't know these start and end dates. So you don't know how to align the series. So then you can't have Fourier terms on a global level. So then you need to do something else, like a decomposition. But in real-world series, yeah, that all are aligned, follow roughly the same patterns. Fourier terms work great. And they will work better than deseasonalization. Good. Yeah, this kind of concludes the part of how to deal with non-stationarity. now I just want to discuss a couple of other issues that you need to take into account when building a machine learning model for forecasting. One is normalization. So how to normalize the series before feeding them into your model. So I would argue there's actually very different forecasting problems. So in some forecasting problems, the forecasts are within a pre-specified domain. So an example could be wind speed. You know that a wind speed will be always between 0 meters per second and 25 meters per second, maybe 30 meters per second, but that's already like a very, very strong storm. And you know, like wind speed will never be 100 meters per second. And then according to that wind power, I mean, a wind turbine has just the minimum and the maximum power it will output. Same electricity price. So electricity prices are usually topped by some regulations. So there could be a regulation, an electricity price cannot be more than $1,000. So in that situation, obviously, you know kind of what to normalize with. But in other situations, it's very different, right? Something like a share price. I mean, where could the share price go, right? Look at or web page hits. You have a web page that for years is between 0 and 100 hits, and then tomorrow it gets 10,000 hits, right? In general, businesses that grow fast, like rideshare applications, social networks, your series are in a certain kind of domain, and then suddenly they just take off. So yeah, and that has big implications on how to normalize a series. Also take into account that if the domain is limited, the scale actually holds information, right? So by normalizing, you lose information. Because, for example, a wind speed, you know, you have 0 wind speed. Now you know, well, in my prediction, the value can only be the same or higher. It can't go down. But if you just normalize with like mean, now you bring it to somewhere in the middle of your domain. Now you don't know that anymore, right? So that's a very obvious case of where the scale has information, but there can be more subtle cases. For example, let's say we talk about a business that grows, right? So if you have a small business, then exponential growth is probably a lot easier to achieve than if your business is already a global company, right? So basically, what does it mean for a small company with 50 customers to triple their sales, whereas a company like Facebook to triple their user base, right? So usually if the level is already very high, the trends tend to be less steep. And well, again, the solution is that if you normalize, you are losing this scale information. So just put information about the scale back in as an additional input. And another consideration is that actually also the error measures that are very often used in time series forecasting, and we're going to get that quite soon. These error measures are often scale invariant. And this can also lead to problems in real-world applications, but we're going to talk about that later. Yeah, so that's just an example of what I mean, that a mean normalization sometimes is a good idea, sometimes it's not. So think about it. What does it mean to do a mean normalization if the series have a strong trend, right? So look at this series. So you see it has this kind of multiplicative seasonality. It's really like growing. And here in red, I'm showing the mean. So what does it now mean if you normalize? So you divide by this mean. It doesn't mean a lot. I mean, here these small values, they will get really small. And these values, they will stay a lot bigger than the other values. So on this series, just dividing by the mean it's not a good idea. So here just, yeah, this type of normalization won't really do any good. Another topic to cover, or to another thing to think about when building machine learning models in forecasting is whether to do direct output versus iterative one step ahead output. So traditional methods like ETS and ARIMA, what they usually do is they just predict one step ahead. That's everything they do. And then if you need 2 steps ahead, you first predict the next step, then you feed that back into the model, and then you predict the next step, and so you go on, iteratively predicting forward. But the problem is that this leads to error accumulation, right? So if your 1 step ahead forecast was wrong, the 2 step is going to be a bit more wrong, and so on. And obviously also, if you want, let's say, a 5 step ahead forecast, it's better to directly optimize for that 5 step ahead and not optimize for 1 step ahead and then just iterating out. So if your method doesn't know you want a 5 step ahead, it can't optimize for that. So there are some results in the literature that argue that it's better to predict directly all the horizons that you need. If you are using a method such as a neural network, that's quite easy because it just can have multiple outputs. So you just have an output window with all the predictions that you want. But if you have methods such as a gradient boosted tree where you can have only one output, then you can go back to this iteration scheme of just predicting 1 step ahead and then iterating out, or you just build a separate model for each horizon, right? So let's say you have a monthly time series and you want to predict the whole next year. So that means in the neural network, you would have an output window of 12 values, or you could just predict always the next month and then kind of iterate out. Or you would build 12 different models, one to predict 1 month ahead, one to predict 2 months ahead, one to predict 3 months ahead, and so on. Yes, because I've already talked quite a bit about gradient boosted trees for forecasting. So they work quite well. They've been now successful in several forecasting competitions, like the JeffCom 2014 competition actually was won by a gradient boosting machine, many Kaggle competitions, and most notably now the recent M5 competition was really dominated by light GBM models. There's another very interesting model, the cut boost algorithm, which performs ordered gradient boosting, and there is especially suitable for time series because, yeah, it respects the order in the data. If you use a gradient boosted tree, seasonality and trend handling can be just done as I've discussed earlier. As also just said, you build one model per horizon. And they are especially suitable if you have many and diverse external variables on very different scales. You know, let's say you have the sales, you have weather data, you have pricing data, you have some consumer indices. You just put that all together, and with the gradient boosted tree, it tends to work quite well. Then what people have been quite successful in the past would be engineer features such as rolling means, rolling standard deviations, or other rolling summary statistics. Differences, as discussed before, you can just use them as additional inputs. So the good thing is you now don't have to decide, do I do differencing or do I feed in the values directly? You can feed both. You can even now feed different differences. So for example, you could do a lag 1 difference and a lag 12 difference. So basically for each value, you take the current value minus the last value, and you take the current value minus, let's say, the value 12 back. So in a monthly series situation, you would basically take you have a February value, you subtract the January value. That's your lag 1 difference, and you take the January value and subtract last year's January value. That gives you the lag 12 difference, and that's all features that you can engineer and feed into the model. And that works quite well. And then, yeah, I mean, feature engineering, obviously, people get quite creative. So you can obviously feed in holiday effects. You can have them one-hot encoded. So you have a variable which tells you which day is Christmas, which day is New Year, or just a variable where you throw all these holidays into one pot and you say, is it a public holiday, yes or no? You could also have distance maps for the holidays, as in today is Christmas, so you have a 0. Yesterday was basically one day before Christmas, so you have a -1, -2, -3. So a variable that encodes how far are you away from such a public holiday. The idea is that because public holidays very often they are not just on the day, but the day before would already be a bit different, and the day afterwards as well. You can do things like that for monthly series, the number of training days in the months, because some months are shorter than others, and in some months you have like 4 public holidays. So that can turn out to be a good feature, and then really people get very creative with feature engineering. Another topic I also wanted to briefly mention is ensembling and forecast combinations. So ensembling works in forecasting just as well as in pretty much any other area. So definitely do ensembling. It has been heavily used in Kaggle competitions. These forecasting competitions have won usually by ensembles of gradient boosted trees, neural networks. You can also use pooled regression in that. We have recently worked with ensembles of local and global models. That works quite well. And yeah, just to recap, that ensembling is well known in the forecasting literature under the keyword forecast combination. There was a seminal paper by Bates and Grunge in 1969, where they basically show that combining forecasts often leads to better accuracy. So this finding has been widely accepted and adopted in the forecasting field since then. And one conclusion from that research is that the simple average is often really hard to beat, even though many more sophisticated methods exist, right? So basically just you build a gradient boosted tree, build a neural network, and then you just do a simple average of the two, and that tends to improve. And obviously there's a lot more research around, well, the methods, they should all be quite accurate. They should all be quite uncorrelated, independent forecasts. People do bagging, people do boosting. So this is a quite interesting research area. So this concludes my part about general machine learning. You've seen I spoke mostly around, well, how to engineer features, how to make machine learning methods deal well with non-stationarity, and how to really kind of do all of this pre-processing type of things that you can use feed-forward neural network, a gradient boosted tree, a support vector machine to do good forecasting. Now, in the next part, I want to talk a bit about deep learning for forecasting. Yeah, so as an overview, so it's going to be just like a small overview, so I'm not going to cover it extensively here. So I hope, yeah, so a recent review is given by Benitez et al. In 2020, and there are some great recent tutorials by Amazon. Definitely check those out as well, where they go really deep into these types of models. So that's why I decided to only cover them here briefly, even though I do know it's a very hot research topic, and many people are probably very keen on really diving deep into those types of models. So as a general observation, what in forecasting in this space is very often done is that people take the most recent research that came out of natural language processing, like LSTMs, attention, transformers, and they adapt that to the time series use case. And that tends to work really well. However, there are some differences to the NLP case. So in forecasting, pretty much always, the most recent observations are more important than the more distant ones. So compare that to NLP, that would mean something like that the last words in a sentence are always more important than the first ones. It's not the case in NLP, but in forecasting. So that's the main difference you need to take into account when doing the modeling. And another thing is that long-term dependencies in forecasting are actually usually relatively simple and stable. It's normally just seasonalities and not really anything else. So very often these NLP models are actually a bit too complex and doing a bit too many things. So for example, attention, right? So people often use like a lot of attention in their models. And then the only thing they usually do if they look at just one time series, very often they just kind of rediscover the seasonality with the attention, which is something, as I discussed before, as a forecaster, you would usually be arguing that the seasonality can be just assumed to be known beforehand. So yeah, just take that a bit into account. And now, yeah, so far I've talked only about autoregression, right? So you just have a window, some lags, and that's everything your model ever sees. But now, obviously, we can go beyond that with recurrent neural networks. So there's a recent overview paper by my team in 2020. The recurrent neural network obviously has an internal state which allows them to memorize. There has been some early work, or well, some work some years ago where it has been shown that they actually do have problems learning long memory. I'm sure you've heard about these vanishing exploding gradient problems. So the LSTM mitigates that to a certain extent. However, they still work better in practice if used with an input and an output window. And that's a finding that Slavik Smil had in his work, and we confirmed that later on in our work. So by using that input and output window, you are essentially making them more autoregressive. So it's basically more like a feed-forward network that just has a state as well. So that has the advantage that the state doesn't need to remember everything. The state is less important, and that we found that tends to work better. And also recent research suggests that in general, recurrent neural networks that can be trained and are stable, they can then be well approximated by feed-forward networks, right? So this is another instance of this. Just because a neural network can learn something in theory, it doesn't mean it's going to learn it in practice. So current neural networks are great in their capabilities, but it's not so easy to really get a neural network that is stable and does what you want. And it turns out that very often, if you can get such a network, you can even get a feed-forward network that is even simpler and does the same thing. However, the recurrent networks have been very successful and yeah, definitely worth looking at, but just keep these considerations into account. Now, talking about convolutional neural networks, recent results suggest that CNNs work just as well as recurrent neural networks for forecasting, but they are a lot faster to train. There have been breakthroughs with things like WaveNet, causal convolutions, and dilations. But obviously the drawback is that the CNNs, just as a feed-forward network, they don't have a state. So basically what's in your input window, that's everything that the CNN knows about. So the input window needs to cover everything. So that means sometimes you need to use quite long input windows, especially if you do the dilations. So if you are in a situation where, let's say, you have some very long series. So you have some products that you sold for the last 5 years, and now you have a product that you just started selling 2 months ago. So then maybe you have time series with hundreds of data points and some time series with only 5 data points. In this situation, actually, an RNN can be preferable, because then you can, like, on the one hand, you have the input window, but on the other hand, also the state encodes the memory. So you don't need to find an input window size that works well globally across all the series. And now in recent years, there have been a lot of specialized architectures, things that work really well. I'm not going to go into detail too much about them. But so there was in 2017 DeepAR, which is a generative recurrent neural network model that is a very successful model. A lot of this research has been coming out of a group of Amazon that do very good work. So you have the deep state space models, which essentially parameterizes a linear state space model with a recurrent neural network. Then you have this paper about deep factors for forecasting, which combines a local probabilistic model and a global time series. That is a linear combination of these factors. So it effectively does a decomposition on a global level. Then you have NBeats, that also works, is a model that seems to work really well, which decomposes the series into basis functions, and then it does residual stacking. So it achieves state-of-the-art accuracy on the M4 data set, but after the M4 had already taken place, and it was actually part of an ensemble of the second place in the M5 competition. So yeah, good architecture to definitely look at. And now recently people start to use transformers for forecasting. There has been this temporal fusion transformers in 2019. Yeah, so there's a lot of very interesting work in this deep learning field. Another field where deep learning is used a lot is not in global modeling, but in multivariate forecasting. Again, I've mentioned that before, but keep in mind that global models are not the same as multivariate models. So in a global models, so in a multivariate model, the series need to be aligned, and they usually also need to have the same length. So you basically feed in all the time series together for a given point in time, whereas in the global model, you feed in one series and the next, and they are all independent. This is a very active research area, mostly because it's not so clear how to scale these methods. So there is good methods around for predicting 2 series together, 5 series together. But now let's say you are a retailer, you want to predict 30,000 products together. It's not so clear how to scale these methods. So what people would usually do is they would have some sort of a sparseness constraint, where they make that each series can interact only with a few other series. Yeah, quite some interesting work has happened there. There is this paper from 2016 where they use matrix factorization with temporal regularization. Then in 2018, the LSTNet paper where they have a CNN that tackles that basically learns at any given point in time across all the series, and then that feeds into an RNN with skip connections. Then we have this paper from 2019. It's called Think Globally, Act Locally. It also does matrix factorization. It's kind of a follow-up on this 2016 paper. And then they do causal convolutions and attention. This is also a quite good paper worth looking at. Then another work from the Amazon group, including Gaussian copulas, and then a paper from 2020, connecting the dots, which uses graph neural networks to do multivariate forecasting. So this concludes my short overview of the deep learning field. I hope it gives you some pointers to dig deeper into this area. And again, yeah, I was able to only briefly cover it because there are many other topics I wanted to cover. The next one being forecast evaluation, because I think this is a topic where it's very important also for machine learners or data scientists that get into forecasting to understand what's the problems there, what has been done historically, and so on. So if you look at, let's say you come with a data science background, you are familiar with what a regression is, then you would probably say, well, I need to fit a model. So I would have some target values that I fit towards. Then I would calculate an error. I would just use a quadratic loss, and then I would just calculate the mean over those and take the square root. That gives me a root mean square error, which is the optimal thing to do under the assumption that your errors are normally distributed. And then you just do a cross-validation, like a k-fold cross-validation, to make good use of your training and test data, so that you get an independent assumption of the error for each instance in your data set. And this is like a well-established standard pipeline in a regression framework. So now we go to forecasting, and it all gets like so much more complex. So it starts off with what's the target value, right? That's very often not clear. It really depends on which value do you want to predict using which other values. So do you want to do one step ahead? Do you have an hourly day series and want to predict the whole next day ahead? So that means you need to predict 24 next values. Do you want to feed in as features just the last 2 days, the last week? So you already have a lot of flexibility here in modeling your problem. And then it just goes on and on. So basically, because errors in forecasting are often not normally distributed, now people would calculate all sorts of other errors, absolute errors, quadratic losses, percentage errors, relative errors, scaled errors, and then you can obviously do means and medians and geometric means and so on of all of those. And then instead of cross-validation, people usually do like out-of-sample evaluation, last block evaluation, where you just say, okay, I train on, let's say, 2 years, and now the last year of data, I just withhold that and do some testing on it. Okay, so let's unpack this a bit and go into the error calculations. Because here the target values, it really depends on what your problem is. So let's start with the errors. So there's a very good overview by Hindman and Köhler from 2006. Maybe surprisingly for people who are not who get started with forecasting, is that this is still a quite controversial area, and there's no solution that always works. And there's still papers come up that just use their own ad hoc error measure. And also error measures are often misused in papers, or well, not often, but sometimes you see a paper where it's not used properly. So the easiest thing to do is obviously a scale-dependent error and error measures. So a scale-dependent error, you could do an absolute error, right, where you just take your true value, you subtract the forecast, you take the absolute of that. Or squared error, you just square that, and then you get quite easily to your root mean square error or your mean absolute error, right? So this is fine, but it has the problem that you now can't compare forecasts across series that are on different scales, right? And in the past, people would like to do that. They would say, well, I have one series that has dollar values, another series that has web page hits, and now I want to have a method that works well on all of them, so I need to somehow compare the methods across these very different series. So we need to somehow normalize or standardize these errors. So the first thing that people came up with were the percentage errors. The idea is, well, let's just divide here by the true value of the series and multiply with 100 so that we get a percentage. And that gave people, and that is what this mean absolute percentage error is, the MAPE. However, the problem is that, so by doing this, at first this looks like a good idea because now you get some sort of, well, are you kind of 10% off, something like that. It seems like a good idea. However, dividing by this YT, it gives you all sorts of problems. So, for example, you cannot use this measure if YT is 0, right? Now you're dividing by 0. And also if this YT is very small, the MAPE gets heavily distorted. So keep in mind that this measure was originally used for inventory count data. So you would always have values that are, 10, 100, 1,000, but you would never have values between 0 and 1, for example. It would be always, counts 1, 2, 10, and so on. So basically, if you normalize your series, and then you have series that are kind of just between 0 and 1, or between -1 and 1, the MAPE is definitely not the right measure to use. And another problem is it is also not symmetric. So if you exchange the prediction and the true value, you change the result, right? So if YT is 3 and YT hat is 5, you get a different result than if YT is 5 and YT hat is 3. So to address some of these problems, people came up with something that is called the symmetric MAPE, sMAPE, where the idea is, well, so we want to make it symmetric so that we can exchange the prediction and the true value and it stays the same. So instead of here dividing just by YT, we divide by the average of YT and YT hat. And you also need to have absolute values here. So it turns out that now you get the symmetry that the MAPE doesn't have, but you break another symmetry in the sense that, let's say your true value is a 3, and now you predict 2 too much, which is 5, or 2 too few, which is 1. These two will give you different errors now, because think about it, you're dividing by the prediction, so the bigger this prediction is, the smaller the sMAPE will be. So you're effectively penalizing over prediction less than under prediction. You still have problems with zeros, because obviously if the actual is a 0 and you have a very good prediction and that is also a 0, you're still dividing by 0. And another, a bit more subtle problem, but that's also very, very relevant, is that if you have a 0 in the data, and that has actually big implications if you have intermittent data, if you have like slow selling products, a product that you sell only once every 2 months, and you have a daily series and you have all these zeros. So now what happens if you have here 0, right? So you have 0, 0, you are effectively dividing YT hat by YT hat. So that means this gives you a 1. So that means no matter what YT hat is, if it's non-zero, you will always get here 200 of sMAPE. So basically, if your series contains zeros, you better make sure you predict an exact 0 and not 0.001, because that will get just the same penalty as 5,000. They are all penalized maximally. Okay, so Suilin in 2017 in his winning solution for a Kaggle competition. Actually, he modified the sMAPE in a way that he basically said, well, if this value down here in the denominator is too small, I just replace it by a value that is a bit bigger. So that's a version of the sMAPE that we often use nowadays. Yeah, so you see, and the sMAPE, it's still very, very commonly used. So it was one of the measures used in the M4, in the M3. So it's pretty much the standard error measure to be used. So yeah, that brings us to the next category, relative errors and relative error measures. So the idea was now, well, okay, so if dividing by the true value gives us so much problems, why don't we use a benchmark method B? And usually people would use just a naive forecast as this benchmark. So now you can get relative errors where you basically divide your error by the error that this benchmark is making. However, you still have problems if true values are zeros, prediction are zeros, benchmark predictions are zeros. So not winning much. And now there is this other idea, relative error measures. So what about, instead of just kind of dividing every error by the error of the benchmark, why don't we just at first calculate the mean over everything? So we get like the mean absolute error, and then we just divide that by the mean absolute error of our benchmark. This is a good idea. It's a good measure. If this is a naive forecast, I think it also tells you a lot, because it tells you that if your measure is above 1, it means you are worse than actually even the naive forecast. So basically, any method that has a rel MAE of above 1 is basically useless. But you do still run into the same problems, because let's say you have many time series, and for each time series you only predict one step ahead, and all these series are on different scales. So now basically over what are you going to calculate the mean? I mean, in order to calculate this rel MAE properly, you need to calculate this mean over like a quite big output window. So you really need to have a bigger test set on a series. If you just predict one value per series, you still have the same problems. You can't really calculate this mean properly. You are kind of back to this situation from before, and it doesn't, yeah, and you can still get your division by 0, for example. Good. So in his in their work from 2006, Hindman and Köhler now came up with a new error measure that solves many of these problems. So they came up with the MASE, the mean absolute scaled error. It's defined as the MAE divided by the MAE of the naive forecast over the training part of the time series. So you take your time series, you take the training part, you take this naive forecast or seasonal naive, both versions exist, and then you divide your errors on the test set by this error that you got over the training set. Now this solves a lot of problems, because your training set will normally not be just one value or two values, and if your whole training set is zeros, then it should be also quite trivial what a good forecast is. So the MASE solves a lot of problems. It's now used as quite a standard measure in many time series forecasting situations. It has been also used as a measure in the M4. However, now you're dividing here by the performance of the naive forecast, and it turns out that the naive forecast, there are certain situations where it works just a lot better than in others. If you have a very smooth series, then taking the last value is obviously a good predictor for the next value. If you have something that is jumping around a lot, like an AR1 process with a negative coefficient, then obviously the naive forecast will be horribly bad. So that means that by having a high or low MASE, it's not necessarily telling you something about how good or bad your model is. It's also telling you about how good and bad the naive forecast is. But obviously, it works well to compare different models on the same series. Yes. So just to sum up this discussion about the error measures. So to get a scale-free measure, we need to divide by a normalizing factor. And now it turns out that due to the potential non-stationarity of the series, it has been really extremely difficult to do this in a way that just works in any situation. So today people use the sMAPE and the MASE as standard error measures. It has been used, for example, in the recent M4 competitions, but you still need to watch out for very small values, intermittent series, and a couple of other issues that we're going to discuss. And so basically, when you build a global model, very often you actually don't want to have a scale-free measure, right? So if you build a global model on all your sales, actually getting the error right on a, so basically you have a series which always have sales around 5,000. Now getting 1% of error on this series means hundreds of units. Whereas if you have another product that you only sell 5 times every day, having a 1% error there is actually very small. So very often so all this work that has been done on scaling the errors, very often you don't need that when you build a global model, because there is actually a meaningful scale. All your series are dollar values. All your series are SKUs, stock keeping units. So, and then sometimes, and then you probably don't want a percentage error per series, but really an error on your scale. You want to say, well, on average, I'm $500 off, right? So I think the message here is really that if you don't need a scale-free measure, then just stick to the MAE, RMSE. They're perfectly fine to evaluate. They don't have all of these problems that many of the other measures introduce. So just use those. And now if you really compare across data sets, then maybe you can find a scaling factor, not per series, but per data set. Okay, that was everything I wanted to say about error measures. Now we come back to the next point, which is how should you split your training and your test set, and how does that work with the training? So yeah, so the most simple thing, or the most straightforward thing to do, and that everybody does, or that comes to mind, is an out of sample evaluation, where you just say, this is my time series, the blue dots are my training set, and now I just cut off a bit from the end of the series, and that's my test set. That's where I test on. And now there are these two different ways of doing things, which is fixed origin, and rolling origin evaluation, and they are very different, okay? So in the fixed origin evaluation, what you do is you basically, so here's your training set, it finishes here, and now you just predict all the points in the test set, but without having any new information. Now what that makes is that obviously the first point in your test set is 1 step ahead prediction, the second one a 2 step ahead, 3 step ahead, and so on. On the other hand, you have the rolling origin evaluation, where basically you forecast the next data point. Now this data point becomes available to you. You predict the next one, it gets available, you predict the next one. So all of these predictions are all 1 step ahead predictions. Yeah, two very different paradigms, especially so just to illustrate how different they are. If you look at a naive forecast, a naive forecast with a fixed origin is obvious. So here is actually 1 data point missing. So the last data point in the test set, in the training set, is up here. So now you basically just copy that over, and this is your forecast. And in fixed origin, obviously, this is going to stay your forecast. So that's what a naive forecast looks like with a fixed origin. And now with a rolling origin, like at every point in time, you always use just the last observation as your forecast for that value. So you are very closely basically just following the series, right? So and this is also where, and again, I want to reiterate 2 points. Always benchmark against the naive forecast and don't trust the plots, because in a rolling origin, these plots always, every forecast looks good in a plot in a rolling origin evaluation. So just, you see they are kind of following the signal, so that plots are good for some sanity checking, to say, yes, the method seems to do something reasonable, but after that you need to calculate errors and you need to benchmark against something, for example, a naive forecast. Good, and now back to the fixed origin evaluation. So what are the advantages of fixed origin evaluation? Well, it's easier to implement than rolling origin, because you train your model once and then you predict forward, and depending on how your model is built, you do that in one way or the other. Forecasting competitions almost always operate like this, because they cannot disclose the test set to you. So they have to tell you, well, I give you the data up to this point, and now everything afterwards you have to predict without getting any new information. The drawback of this is that this is not how we usually operate in practice. In practice, you usually need to give today a forecast for tomorrow, tomorrow a forecast for the day after tomorrow, and so on. So you roll forward. Another big drawback is that now you can only evaluate one forecast per horizon, right? So what we've seen before. So here, this is 1 step, 2 steps, 3 steps. So they are all on different horizons. So you have really only one forecast for this horizon and for this time series. And so it's often difficult to capture the full picture, because if you have to do all the predictions from one day, let's say, now how far out are you going to predict from that day? You are probably not going to predict a whole year. So you're going to predict only, let's say, 4 weeks out. So if in these 4 weeks you don't have Christmas or the summer holidays, you actually only get a partial picture of how well your method works. So rolling origin is better in that sense. However, it can be difficult to implement, especially with some of the traditional methods, because they often are implemented in a way that they require to be retrained for every forecast they make. It is much more natural to implement with machine learning methods, where it's basically normal that you just train your model and now you get some new data and you just use that model without retraining. And rolling origin, it becomes even more important in global modeling, because where all the series are in sync with their timestamps. Because what I just said about Christmas, summer holidays, and so on. So now this really, so on a data set like the M4, where all the data comes from different origins and different sources, obviously some data points would be some series would be just before Christmas, others not. So you get a bit of a mix of everything. But if all your series are aligned, then of course, to get the full picture, you need to really do some sort of rolling origin evaluation over a whole season to really know how your model will behave, yeah, on things like Christmas, summer holidays, and so on. However, you really now need to be aware of leakage from the training to the test set. So because you now kind of, after every forecast, you take that point and make it available to the method. Yeah, it has happened to me, it has happened to pretty much any forecaster I know, that at some point you just get a very good forecast and it's just that you did something wrong and evaluated something again, and you only did a 2 step ahead forecast but you wanted to do a 5-step ahead forecast, and just for some reason you were feeding in data from before. So yeah, it's data leakage can be quite a problem in this rolling origin evaluation. And also this type of rolling origin evaluation, as I've shown, that is sometimes called time series cross-validation. Yeah, so just some kind of other ways how to do things. So there is this two-slide variation on the rolling origin evaluation. One is this expanding window where you basically your time series grows and grows with every data point and gets longer. And the other one is the fixed window approach, where basically the last data points, you just drop them completely. Yeah, and the expanding window is better if you don't have a lot of data available. And you can also combine the two. You start off with an expanding window, and then once the window is already quite long, you just use a fixed window going forward. Okay, so now we've seen the rolling origin evaluation. This is also called time series cross-validation. But now the question is, why don't we just do let's say a normal k-fold cross-validation as we know it? So that would mean that instead of just using this part from the end of the series to do your forecast, you just pick randomly data in your series and you assign them to here 5 folds, and now you train, right? I mean, it looks a bit not like a good idea, because so there's obviously, if you do that, there's problems of serial correlation between the data, right? So every day, so today's value probably has a lot to do with yesterday's values and tomorrow's value. And you also have problems of non-stationarity. So basically, so let's say you are testing always, you pick all the Mondays to be in the test set and you never pick any Sunday, you obviously won't get the full picture, right? And also in this scheme, you're effectively having data in your training set that are later than the points in your test set. So you're effectively training on the future and then predict the past. So it just doesn't feel like a good idea to do this type of cross-validation. So there is this fear that cross-validation will grossly underestimate the generalization error if you do that. And there's another problem with cross-validation. Most traditional methods and also RNNs that kind of evolve a state going forward, they often don't deal well with missing data, because here obviously these orange data points, they would be in the test set. So in your training set, they would be just missing. You can't use them. Yeah, so that's why people don't normally do cross-validation. However, there are some ways around these problems. So people in the literature have proposed all different sorts of cross-validation types for time series. So ideas have been to use blocks, right? So basically you put your training and your test folds, you make them continuous blocks in time. That's something I've done some research as well on. It obviously helps you around the serial correlation, but it doesn't help you around the non-stationarity. Another way of doing things to get around serial correlation is you just, whenever you have a training point in the test set, you just remove points around it from the training set. But now you obviously have the problem that, well, you can lose a lot of data. So, and obviously the whole idea of cross-validation is making good use of your data. So losing a lot of data doesn't seem like a good idea. But obviously all of these only address serial correlation problems. They don't really address any problems with non-stationarity. But they are still often a good idea doing. It looks a bit different when we look at pure autoregressive models, because now think about it. So you've done your windowing, you've embedded your time series into this matrix form. So now really nobody stops you from just randomly partitioning your data into a training and a test set in this matrix. And certainly your method is going to work just well. I mean, you just remove these rows from training, and a purely autoregressive model will work just fine. So that's some work I've done in the past. So we developed a theoretical proof that cross-validation actually performs well in such a purely autoregressive setup as long as the models nest or approximate the true model. Because then the errors are uncorrelated, and that's everything that matters. So as long as the errors are uncorrelated, the cross-validation is going to work fine. And it's actually a quite relevant result because many, as we've seen before, many machine learning models would just have only an input window. That's everything they see. So then you can do cross-validation, especially to detect overfitting. So the cross-validation will not underestimate your generalization error if your model overfits. And arguably, that's usually the important part, to detect overfitting, because underfitting can be detected separately and quite easily by a test for serial correlation. And this is also implemented in the forecast package, this function. And yeah, so because I just mentioned a test for serial correlation, so there's this Ljung box test for serial correlation, which detects serial correlation in the residuals, and that means that your model is underfitting, right? So as I just said, it can be used together with the cross-validation, so that at first you use this test to detect underfitting, then you do the cross-validation to detect overfitting. But I think more in general, it's really a good idea to just look at the residuals that you're getting from your model and then check, is there autocorrelation there? Are there any seasonal patterns, anything I can see in the residuals? Because if yes, then that means that your model is still not using all the information available in the data, and you can still improve your model. So residual diagnostics is a quite good thing to do in forecasting. This brings me now to the next section, which is about probabilistic forecasting. So there's essentially a couple of ways. So probabilistic forecasting is a very important topic now as well, because very often you are not really interested in just getting a point forecast, but you really also want to get an idea of how much uncertainty is in your prediction. And there's a couple of different ways of getting to probabilistic forecasts. You can do analytical prediction intervals, you can do bootstrapping or MCMC sampling, you can forecast the parameters of a distribution, you can use quantile regression, or you can determine the prediction intervals just empirically through backtesting. I'm going to go quickly through these different options. So analytical prediction intervals, that's obviously possible if you have a well understood model and you can calculate them. Actually, many of the classical models do this. So ETS, ARIMA, they will directly give you prediction intervals. However, they often have the well-known problem that these intervals tend to be too narrow. So they don't consider all sources of uncertainty, so they are a bit too narrow. Another thing to do is something like bootstrapping or MCMC sampling. That tends to be often quite slow. The intervals can also be too narrow depending on how you do it. For example, if you train your model, if you have a neural network and the only thing you do is you change the initial weights, then the only thing you are considering is the parameter uncertainty of these initial weights. You're not considering data uncertainty, you're not considering the model uncertainty. So then your intervals will be also too narrow. With MCMC sampling, Bayesian methods, people actually get quite good results in terms of prediction intervals. Determining the uncertainty empirically through backtesting. So this is very often used by companies in practice. It leads to more realistic prediction intervals. They don't have this problem of being too narrow so much. The problem is more that you need a lot of past data, you need to do rolling origin forecasts, so it's also not feasible to do this always. Now another way how to do probabilistic forecasting is to estimate the parameters of to forecast the parameters of a distribution. So for example, you can assume that your predictions will be normally distributed, so you just predict the mean and variance of a normal distribution. That's something that, for example, deep AR does. And you can use deep AR with a normal distribution and a negative binomial distribution. Well, that's what the original paper shows results for. That you can also use it with other distributions. The drawback of this is now you have to assume a certain distribution beforehand, and that's good if you have limited amounts of data available or if you have knowledge of this distribution. But if you have a lot of data and you don't know anything about the distribution, this may also not be the right thing to do. And this brings us to the quantile regression with pinball loss. So this is also nowadays done by many people, for example, implemented here in this work by Wen et al. From 2017. The advantage is you don't have any distribution assumptions. So you don't need to make any distribution assumptions. So it is good if you have a lot of data available. It's fast to compute and usually quite easy to implement. A drawback is that you can only obtain certain quantiles, not the full distribution. However, in practice, usually something like 5 or 7 quantiles would be enough anyway. And then if you do use, for example, a neural network, you can just fit different quantiles at the same time by having multiple outputs. And then you actually get a quite decent probabilistic forecasting model. There has been also work in the past where about interpolating between these quantiles with spline interpolation, and then you actually do get a full distribution out of such a model. Yeah, just to go a bit deeper into this, the pinball loss function, what is it actually? So you see here, y is the true forecast, y is the true value, y hat is the forecast, tau is your target quantile, and now basically you penalize the forecasts different whether you over forecast or under forecast. And now there's theoretical results that prove that minimizing this loss function actually results in the most accurate quantile. So just as an illustration, this is how this loss function looks like. So it's asymmetric. So basically, in one direction, the loss grows slower than in the other direction. And that now obviously all depends on the quantile you try to predict, right? So basically, if you predict different quantiles, this loss function changes. Now, obviously, how to evaluate probabilistic forecasts, that could be probably a whole new section, but I'm going to only briefly look at this here. So a very simple way to evaluate a forecast, with a probabilistic forecast, would be a hit-miss rule. So this is directly interpretable, right? So you basically just say, well, 80% of the forecasts so you predict an 80% forecasting interval, and now you just check, well, in the future, are 80% of my values inside of that interval and 20% outside of that interval? Then you say, well, that's a good forecasting interval then. However, this has the problem that you don't consider the magnitude of the error, right? You just say, is it inside of the interval, yes or no? And now this has the problem that trivial solutions are actually possible. You can just, in, let's say, 80% of the time, grossly overpredict, have a very big interval, and then in 20% of the times have a very narrow interval, and then trivially 80% of the time values are inside, and 80% of the time they are inside, and 20% of the time they are outside of the interval. So yeah, that has some obvious shortcomings. So there has been a lot of research into how to do it better. There is this mean scaled interval score, which was used, for example, in the M4 competition. So it is like this hit-miss rule. However, when you miss, when your forecast is outside of the interval, for all of the forecasts that are outside of the interval, you sum the size of by how much they were outside of the interval. Yeah, so that works. And then another thing that is often used is the continuous ranked probability score. So this hit-miss rule and this MSIS, that's only workable for one prediction interval, two quantiles. So this CRPS, it integrates over all the quantiles, and it's essentially a generalization of the MAE to the probabilistic case. And then there are a couple of other scores like the logarithmic score, energy score, variogram score that also have other advantages, disadvantages, but I won't go into detail with that. So this brings me to the very last part of this tutorial. I wanted to discuss two special forecasting problems, namely intermittent time series and hierarchical time series. So let me start off with the intermittent time series. So intermittent data means you have a lot of zeros in your series. And now the way how to deal with that would be, for example, with a zero inflated model, which means essentially you have two models. One model that predicts the probability for the next value to be zero or not. And then you have a second model that predicts what is this next value going to be under the assumption that it's going to be non-zero. And then there is this very standard method that is used very often in forecasting called Croston's method, which is essentially just such a type of zero inflated model, and it uses simple exponential smoothing to make both of these predictions. Another way how to deal with intermittent data is you can use a specialized loss function, for example, a negative binomial loss function like it's used in DeepAR. You could have a Poisson loss function, or you can use a Tweedy loss function that seems to work quite well. And now one thing which, well, it's more some sort of a heuristic, so don't take it as proven, but it seems that different models work better depending on the degree of intermittency. So as a rule of thumb, if you have over 90% of zeros, a zero inflated model is probably a good idea, whereas if your zeros are only, let's say, 30, 40, 50% of the data, an adapted loss function should work better. Good. Speaking about hierarchical forecasting, so hierarchical forecasting, it's a very common problem in forecasting where the idea is that the forecasts need to add up, right? So they need to add up, for example, spatially across stores, distribution centers, countries. So you sell a certain product in all of your stores. Now, obviously, you know that the sales across all stores add up to what came out of your distribution center, and the sales across all distribution centers add up to the country level. Also across product categories, you know that all the different brands of milk that you sell need to add up to your overall milk sales, right? So different product categories, different store departments, and so on. And you can also add up temporally, which means that you know that the sales on weekly need to add up to your monthly sales, need to add up to your yearly sales. There's a quite nice recent overview in a keynote speech from Rob Hindman, if you want to delve deeper into this topic. And now, what are the classic approaches to do this hierarchical forecasting? Well, there's a top-down approach where you just say, let's predict this single series at the top, but now you need to somehow disaggregate these forecasts to the lower levels. So now obviously you have this problem, well, how can we disaggregate? Well, you can say in the past, this product made up 30% of my sales, and this product made 20% of my sales. You can also train a model, a machine learning model to do this disaggregation, things like that. Bottom-up forecast, it's the other way around. You predict all the series on the bottom, so you predict the sales of all the single products, for example. And now the only thing you have to do is you aggregate them all up. You sum up all these forecasts. The problem now is that the bottom level series, they very often have a lot of noise and you don't see clear patterns of seasonality and trend. Your sales are sparse, lots of zeros. So yeah, very often there's not very nice patterns to extract. So people came up with this idea of a middle out forecasting, where we basically just predict all the series at a middle level, and then you aggregate up and you disaggregate down. Now in 2011, there was this paper that introduced now the optimal reconciliation. So the idea is, instead of doing top down, bottom up, middle out, we forecast all the series across the hierarchy. And now we get all these forecasts, but these forecasts now they don't add up correctly, right? So, well, so now that we have all these forecasts, let's have a subsequent step that is called a reconciliation step. And it's least square optimization, where we now just change the forecasts, all the forecasts a little bit so that they add up. And it actually turns out that this leads to more accurate forecasts than the classical approaches. And since 2011, a lot of research and theoretical insights have been in the forecasting literature. So, for example, there has been this paper about trace minimization. That is a very important one. And also recently, people have started to develop a geometric view of this hierarchical forecasting, where they basically say forecasts must lie on a coherent subspace where linear constraints hold. Yeah, so this is still a quite active research area in the forecasting space. And now, to make it even more complex, obviously, you could now want to have probabilistic hierarchical forecasting. So now the question is, well, what does forecasts add up correctly across the hierarchy mean in a probabilistic sense? So there's this very recent work from 2020 where the answer that they give is, again, with this geometric view, well, the multivariate density just must lie on a coherent subspace. And there has been also quite some nice work in the machine learning community around this probabilistic hierarchical forecasting. Yeah, but this is a very interesting problem. So just to sum up the hierarchical forecasting, I think in this area there's still a lot of very interesting research possibilities for machine learning, especially on methods that directly produce a reconciled forecast in one step, so that you don't have to at first forecast and then reconcile, but you somehow build it all together into one model so that the forecasts you get out directly are coherent and add up across the hierarchy. So this, now I'm nearly at the end of the presentation. I think it's time for some conclusions. So just as an overall summary, forecasting as a field has come a really long way. It's a great time to do forecasting as a machine learner or data scientist. Machine learning methods become more and more competitive. We have a lot of really good answers for problems in this space. But also be aware of some of the common pitfalls in forecasting. And I hope I could clarify some of these things so that less people fall in these traps around evaluation, benchmarking, data leakage, different types of non-stationarity and how to deal with them. Yeah, and with that, the only thing I want to wish you is happy forecasting. And finally, I just want to thank, obviously, a whole lot of people that have worked with me on all of these interesting problems throughout the years. So all my collaborators, but in particular my PhD students, Kasum Bandara, Hansika Heva-Malage, Rakshita Godaheva, and Dilini Rakshak-Paksha for all the hard work they have been doing, and all the interesting and good work that we are doing. And with that, I want to thank all of you to attend this tutorial presentation. Have a look at my website, cbergmeir.com, or write me an email to my Monash email address. So thank you. I finally proceed to show the reference slides so that they're also in here. And with that, see you soon.